Hello, my name is Robert Carbon and I'm presenting today an innovative approach for a goal-oriented architecture for telescope control software. Let's first look at the current state of practice for telescope control software. So we face a number of challenges handling those complex systems. Telescopes are typically one-off experimental machines with a substantial emergent behavior which comes together once the system is integrated of all these different subsystems that require coordination and have to support many different operational modes and wavefront control strategies. Due to their long lifetime, ranging from 10 to 50 years, the systems often evolve substantially over that time frame, with sometimes significant modifications to the control strategy and the hardware. The next generation of extremely large telescopes also has to deal with the explosion of scale. The number of I/O points and actuators and sensors increase typically by a magnitude, order of magnitude. Due to that new scale, there is also an increased risk of component failures due to that scale. So the control strategy must be flexible and adaptable to deal with those failures and hardware and system reconfiguration. The humans in the loop, such as the operator, can get easily overwhelmed by the available information that is required to make the right operational decisions. On top of that, we have to deal with a multitude of interacting distributed control loops with hundreds of connections, and they often have implicit and explicit dependencies which have to be considered when modifications are required. And last but not least, it's quite difficult to tune those individual loops and then integrate them end to end so they work seamlessly together. So let's look at the goal-oriented and state-based architecture. The analogy we draw here is with Google Maps. So imagine you're driving a car and you have some destinations and deadlines. You have to plan a route to get from A to B, and you rely on gauges and your own senses to get from A to B. Now, by entering a destination into Google Maps, you actually formulate a requirement to get from A to B, and the route is planned based on the location and certain constraints, such as the traffic, road work, your actual location. And you receive, as a driver, you receive goals based on those constraints and the state of your environment. So Google Maps acts in that case as a goal planner, and the driver becomes a control system and the car a system under control. Subsequently, the driver tries to do the best to follow those directions by monitoring the environment and the car and also interacting with the car. The driver has to maintain the speed, has to observe the location, the fuel level, and all those elements are called state variables. Those are dynamic properties that change over time. Now, if the driver fails to achieve a goal, for example, misses a right turn on a traffic stop, Google Maps will act as a goal plan and reschedule the route and give the driver a new goal. And if you replace yourself with a robot, nothing really changes for a goal-oriented operation. So the important point for the goal-oriented operation is that the system tells you what to do, not how to do it. It just tells you how to turn right, not exactly what to do to turn right. So the driver has some model of the world to anticipate the behavior and reactions from that environment, like the car. When you hit the accelerator pedal, you anticipate a certain acceleration of the car. So you make some estimations of your environment and the car with your model, and you control your car based on that model. And that's called the control diamond. So the objectives of this goal-oriented control framework that we are presenting here is to capture an executable set of requirements that are expressed as goals, to have a more precise description of what we want to do. We use an end-to-end system model to develop the control architecture, following some principles for the design to implement the control strategies developed by the systems engineers. We also want to integrate the control strategies and operations, which are sometimes developed in silos, and also to enable the traceability from operation scenarios to component behavior, and also to code eventually. The system model will allow us to perform analysis of the operation scenarios and the component behavior and facilitate the end-to-end system testing and tuning. We can produce timelines of the system states and resource profiles, such as for power, and we will apply a low-code approach for the development of the control software. How does this framework look like? How do we capture that? So typically we start with a set of requirements, of the actual requirements, and goals are specifications of behaviors derived from an analysis of those requirements. Such as in this example, we have a requirement for pointing and tracking and synchronous dome rotation, and we derive a goal which is called track on target. So there can be many goals, and if you combine them together in some network, then we are talking about a scenario. For example, a particular observation mode that requires track on target. Now the goals are refined by so-called procedures. So procedures are kind of behavior depending on they're selected depending on some conditions. For example, if a certain accuracy is required for tracking on target, you can either choose blind tracking on target or to have a guided tracking on target. But the goal actually doesn't change. Only the specification of the goal changes for the planner. We still want to track, but sometimes with different accuracies or different specification. The how is left all to the control system. Now, in order to identify those goals, we have also to identify the so-called state variables. So the state variables are the relevant, describing the relevant physical states of the system that we need to control or that affect the control. So here's an example of the true telescope pointing on sky in Alt-A. So there is also typically a reference frame attached to it. And that true telescope pointing is affected by the azimuth position, the altitude position, the observer's position on Earth, and so on. And it affects the science wavefront on the science detector. So the arrows that you see here are the direction of the effect that we exercise. Now, when we identify a goal, it usually is, or it is related to a particular state variable. And if you define a goal for one state variable, we also have to subsequently identify all the goals of the affecting state variables. So we don't forget anything that might affect, that helps to achieve that goal. Right? So we have to have this end-to-end knowledge model of all the physical states and their effects to have a comprehensive control. The goal-oriented system architecture is broken down here in this example as part of the overall product breakdown structure. And the control systems exercise control over certain state variables which belong to a subsystem. In this example, the main structure has an encoder, and the encoder has some state variable which is the encoder health, which is relevant for the main structure control. And the control systems themselves are composed of controllers, estimators, and hardware adapters. So you see here again this control diamond. Estimators use measurements from the hardware to estimate the state variable, and based on the goal, commands are sent to the hardware to achieve the goal based on the state variables. The component behavior is described as a state machine. In this simple case, we just switch between idle, slowing, and tracking. And the state variables, in this case, a discrete one, the encoder health is also described as a state variable. And in this simple case, we have only two stages, which are good and bad. Now, having this description of the operational behavior in terms of goals and procedures and the component behavior, we can run system-level simulation to validate the requirements and generate such a sequence diagram that you see here, where events are injected, the encoder health state variable changes over time, and also the control system state machine changes over time. And we can produce the sequence diagram, see how the components interact, and also a timeline showing in which state we are across the whole board. Based on this system level model, we prototyped a design and implementation following those specified behaviors. So the requirements and objectives for this prototype were to prove a goal-oriented design and implementation for the control of the dome and the main structure, guided by the state analysis architectural principles that I explained before. The focus is on function, not the performance, to demonstrate the interaction between components and validate that goal-oriented approach. We demonstrate the suitability to analyze and model the domain concepts of typical ground-based astronomy functions such as pointing, tracking, offsetting, and dome control. The platform we used for application design is based on state machines for the lifecycle management of controllers and estimators using an World Wide Web state chart XML engine interpreter. The do activities implement the domain-specific goal handling and also the interaction with the hardware, such as commands and measurements. The platform is based on Java and C++ running on Windows with a messaging system using RabbitMQ. SLALib is used for astronomical calculations, and the standard ISO access controller, which was generated from Simulink, is used to implement the azimuth and altitude control. There we have two kinds of model transformations, from conceptual design to low-level design, and from low-level design to low-code, using the framework which is called Komodo. On this slide, you see some screenshot of the UIs that have been developed. On the left side, you see the different timelines for altitude, azimuth, and dome position. You see the scenarios at the bottom to preset track, instrument pointing correction, telescope pointing corrections, and in the middle you see the number of state variables like alt-a state variable, azimuth position state variable, the goals which are currently in place to constrain those state variables, their specification and their status. So the UI interacts with the low code created from Komodo. Overall, we have two things. We have an end-to-end model based on the state effects models representing the end-to-end knowledge, which enable a reconfiguration, rescheduling of goals to adjust to new situations. So we can dynamically adjust the behavior at runtime without going into implementation details at the high level, which itself enables an end-to-end tuning, because we care about the goals at the high level, but not how this goal is achieved. And that delivers us a consistent system and software model and the associated code. The separation of the architectural concerns of the control system and system under control gives us state variables which pertain to the system under control only, goals which pertain to the control only, and the goal-oriented architecture guides the design, allowing for a much better integration of the operational needs with the low-level control in a systematic way. So that facilitates also the adaptation to a changing environment. The state-based pattern, such as the control diamond, allows to extend the control system architecture in a consistent and systematic manner. For future work, we want to capture the whole astronomical environment in the system model, which includes the physics, the rules, and the environment, and also specify the architecture layers more explicitly, such as the observation planning, instrument operation, telescope operation, and the motion control. And overall, we want to establish a reference framework for goal-oriented telescope architecture, similar to the reference frame, to the frameworks which exist for autonomous car control. Thank you very much.